Alright, so for my work energy video reassessment, basically I chose a problem straight out of a book, a straightforward problem, got right to the point, covered the basic concepts of, working potential energy. So it was basically problem 4.5 out of the book. So problem reads, alright, consider a mass M in a uniform gravitational field G, so that the force on M is mg, where G is a constant vector pointing vertically down. If the mass moves by an arbitrary path from point 1 to point 2, show that the work done by gravity is equal to negative mgh, where h is the vertical height gained between points 1 and 2. Use this result. So basically problem A has two parts. The second part of part A says use this result to prove that the force of gravity is conservative, at least in a region small enough so that G can be considered constant. Alright, so I'm going to just go on right to that. Alright, so basically I just, I tried to draw like a free body diagram basically as the problem said. So basically the main thing what I'm trying to do is show that the work done by gravity is negative mgh on basically this mass that's following an arbitrary path from point 1 to point 2. So basically this is the mass, this is like a little dot right here. And I'm saying, alright, so we said G is a vector pointing downwards, and then the force on the mass is mg, which is just mass times the gravitational constant. So therefore, just going through it in my head, I wrote this work is equal to force times this. I mean, that's just the basic way when you think about work. But the work done by the gravitational force is the integral of F dotted into the dr, where dr is the path that the mass is taking. So therefore I just changed my integral. The integral is following basically just a y path. This is moving in the vertical direction. The integral is going from y1 to y2, which is just from point 1 to point 2. It's not moving in the x direction. The force is mg, as we said earlier, and then the path is just dy. It's changing in the y direction. Since mg is a constant, I could take that outside of the integral, and therefore my integral just becomes mg, or negative mg, on the integral of dy over y1 and y2. So therefore we have negative mg, and then the integral of dy is just y from y1 and y2. So therefore we're gonna have negative we have mg y2 minus y1. Yeah, I said negative earlier, but the negative sign doesn't come in till here. Sorry about that. But yeah, there. So now we have mg y2 minus y1. We can take that negative outside, sign out, and make that mg y1 minus y2. And we know that's just basically just h. The change between y1 and y2 is just h. So therefore, we prove that it is equal to negative mgh. So, alright, then the second part of problem A says use this to show that the force of gravity is conservative to use this to show that the force of gravity is conservative. Okay. So alright, so basically for a force to be conservative, it has to meet the two conditions. So the two conditions is the force must depend only on the particle's position, and then the second condition is for any 2 points, 1 and 2, the work done by the force must be the same for all paths. So for the first condition, we already see that the force must depend only on the particle's position, because we don't have really anything else to go by. We don't have the particle isn't accelerating or anything like that. The only thing that the gravitational force depends on is the particle's position. So, and then next, for any 2 points, 1 and 2, the work done by a force must be the same for all paths. So really the only thing that's changing it is the work is h. You get what I'm saying? Because the work is equal to negative mgh. So therefore m is a constant, g is a constant. So the only thing that's changing is h, and no matter what path you take, h is going to be the same. So therefore that proves out to be true. So therefore the force done by gravity is conservative. Alright, and that's it. I'm approaching 5 minutes. Part B was pretty quick, so I'm going to just show that. Basically, I just proved that the gravitational potential energy is equal to mgy. That's all the question asked. And that's pretty much it.